Okay, welcome to Friday of week 2 for the linear algebra class. And we have a pretty important item to discuss today. And let me share my screen and that will show you what's going on. So the plan today is we're going to start out by answering questions. As always, that shouldn't be a big surprise. So if you have questions on the homework or anything else, I can help you out. But when I say start out, I mean start out after I go over the agenda. So I do the agenda first. And then after that, we're getting into a major topic in this class. It's a biggie with lots of applications, and that is determinants. So we'll start out with the easiest possible determinant there is, and that is the determinant of a 1-by-1 matrix. So hopefully you'll all smile because it's that easy. Then what we'll do is we'll define what it means to be the ijth minor of a matrix. And then after that, we'll talk about what it means to be the ijth cofactor of a matrix. And then once we have these minors and cofactors, we'll be ready to define the determinant. And what I thought I would do is actually I wrote some computer code. Sometimes they call it pseudocode because I didn't use a particular language or anything, but basically it's computer code. Because the determinant is actually defined as a step-by-step iterative process. And I'm going to show you what it looks like as a computer code, and I'll also talk about what it is if you hate coding. Then we'll get into the determinant of a 2-by-2 matrix. So those are easy and important. So it turns out 1-by-1 is nothing. You'll all laugh at it. 2-by-2 is a formula that's not too hard, but you want to memorize it. 3-by-3, the formula gets really rough and you're not going to memorize it. Instead, you're going to learn how to find the determinant using the definition and other ways also. So the more examples are 3-by-3 and 4-by-4, etc. Okay. And by the way, today, anything I talk about, I didn't write it out because it's always going to be the same today, is we're only dealing with square matrices. If you don't have a square matrix, you can't even do this stuff. So we're only doing square matrices. So I'm not writing let A be a square matrix in every single sentence, but I'm inferring that A is a square matrix in everything we do today. Then we'll talk about if you have a triangular matrix, and I'll define triangular matrix. It turns out the determinant is really easy and you'll like it. Then we'll talk about, well, if we have a matrix and we know its determinant and we do a row operation to it, how does that change the determinant for each of the 3 row operations? And then we'll find a formula for the determinant of A times B, and then the determinant of the transpose of A, and then the determinant for the inverse of A. And then finally, we'll end with saying, let's see if instead of using the definition of the determinant, let's see if we can just get the determinant using row operations and be done with it. So that's the plan for the day. I want to give you a reminder, and that is Monday is a day off. So there is no lecture on Monday. Go have fun, whatever. The skiing is going to be terrible. But
is our assignment from today due on Monday still?
It's due on Wednesday.
Okay. All right, cool.
Yeah, the assignment, there's no assignment due on Monday. Let's put it that way. So there's an assignment due pretty much every day that we have regular class, Zoom lecture class. And there's no assignments due on exam days either because there's no Zoom class. I think there might be 1 or 2 right after class. There's no assignment, right after the test. But otherwise, every time we have a Zoom lecture, then there's going to be an assignment. Okay, so Victor got in with his question, which can we go over question 59, part B? So let me look at it. Let me go find it. Oh, look at that. Front and center. I know you can't see it, but it happens to be front and center of my screen. Okay, and what I'm going to read it and then I'll type it out is let A equals 1, 2, 1, 0, 5, 1, 2, negative 1, 4. Suppose a row operation is applied to A and the result is 1, 2, 1, 0, 5, 1, 1, negative a half 2. And first find the elementary matrix such that EA equals B, and then find the inverse of E. Okay, such that E inverse B equals A. All right, so let me, I think the easiest, because I don't want to type this thing out, but I think what I'm going to do is going to take about 10 to 15 seconds. Come on, computer. Oh, I wonder if it's under the Zoom thing. I was going to do a screen capture. Oh, come on. It's in there somewhere, but I think it's behind Zoom. Where is it? Sorry. There it is. It's kind of a pain to use Zoom sometimes. Oops. Let's try again one more time. Thought this was going to be easier than it is. That I was wrong. Did it work? Almost. Well, it missed some of the top. I did a little screen capture. So that's a 1, 2, 1 on the top, and that's actually not that big a deal. Just notice it didn't change. Okay, so part A is to find the elementary matrix E such that EA equals B. So the key is to say, to go from A to B, what did you have to do? Kind of in words.
Apply the same row operation to the identity matrix.
But what row operation do we do? That's what I'm saying.
Oh, multiply the third row by 1/2.
Okay, so that's what we're doing. We're multiplying the third row by 1/2, negative 1/2. And that's all it's done. It's elementary, right? So the good news is
negative 1/2. It's just 1/2. Because A has a negative, like it doesn't switch any of the signs.
You're right. You're right.
Okay.
It's just 1/2. Okay. So we're multiplying. So the nice thing, and this is something we did last time, I mean, we did in the lecture, is that how do you get the elementary matrix that corresponds to multiplying the third row by 1/2?
Do the same operation to the identity.
Exactly. We do exactly the same thing to the identity. So then I just go ahead and do that thing to the identity, which means I need to multiply the third row by 1/2. So we have 1, 0, 0, 0, 1, 0. And then normally I'd have 0, 0, 1, but if I multiply by 1/2, I get 0, 0, 1/2. And I guess I should call it E. Was that easier than you thought?
Yeah, but I think the problem is when I calculate the inverse and then I try to multiply by B, the result is not A for me.
Okay, well, let's get the inverse. And the inverse is undoing it, right? Do you agree?
Yeah.
So to undo, multiply the third row by 1/2, what do I have to do?
Multiply the third by 2.
Exactly. So that's all I do is I start out with the identity, multiply the third row by 2. So E inverse instead of a half, I get a 2 there. Does that make sense?
Okay, I see.
So now you can go and say, what is E inverse times B? Well, if you have 1, 0, 1 dotted with 1, 0, 0, you get 1. That didn't change. If you have 1, 0, sorry, it's E inverse times B, yeah. So if you have 1, 0, 1, and you dot that with 0, 1, 0, you get 0. Let's see, 1, 0, 1, yep, and that's the 0 right there. And if you have 1, 0, 1, and you dot it with 0, 0, 2, you get the 2 from A, which is what you want. So you can verify that when you multiply, it actually works. Is that make sense, or are you still lost or confused?
No, that makes sense. I was doing the procedure to find the inverse with adding the identity to the right, and
You could
then
do that. That's a lot harder.
yeah, it's a lot harder.
Yeah. Just when you have an elementary matrix, finding the inverse is really easy. You just undo the elementary matrix, especially when it's a multiply or a switch. It's a little bit harder if it's a combine 2 rows into and replace. But this isn't one of those, so it's easy. Okay. And by the way, if you do take E and you adjoin it with the identity and then you RREF, you really should get this. You might have made some arithmetic mistake or something, but you should get 1, 0, 0, 0, 1, 0, and 0, 0, 2 for the rest. Any questions on that? All right, there's a request to go over 44. So let me go find that one. So just a second. Now I have to go and find 44. Okay, so use the inverse of the matrix. Using the inverse of the matrix, find the solution to the systems. Okay, and there's 2 different solutions. One has a right-hand side 1, 2, and the other 2, 0. And then it said, now give the solution in terms of A and B. Which part did you have trouble with? There's really 3 parts, A, B, and finish it off. Cesar? Okay, A. So I'll do A, because the hope is if you can do A, you can do B, because they're really the same. All right, so what I'm going to do is I'm going to, hopefully this will work faster this time. Okay, so here is the equation that we're given, and we want to solve this. I like to write it in symbols instead of, with all the numbers and stuff. And I'm just going to write AV equals, I don't know, capital B. Actually, it should be lowercase b. Okay, so the idea is if you have a matrix times a vector equals a vector, and you want to solve, what can I do to both sides?
Multiply them by the inverse of A.
Uh-huh. Mm-hmm. Yeah, so I'm going to multiply by the inverse of A. And what I get is that V is equal to, let's write it in math font. So we get V is equal to A inverse times B. Any questions so far? Okay, that's the setup. Let's make this a new page. All right, so what we need to do is we need to find the inverse so that we can multiply that inverse by b. And do you remember I told you there was a nice formula for the inverse that we can use? And that is you do 2 times 1 minus 4 times 1 is -2. So I'm going to write, let's write this out. So we get -1/2, because it's 1 over that. And then you multiply it, if you remember, by the matrix where you switch the diagonals. So you get 1 and 2. And you make the off diagonals negative. You get -1 and -4. Any questions to that? Okay, so that, I guess I should write down what it is. That's A inverse. That equals that. I can multiply the 1/2 through, but I don't need to. I can do that at the very, very end. It's a little easier. But is that clear so far? Have I done anything weird? Okay, again, you can adjoin it with the identity and then RREF. But when you have a 2 by 2, it's so much easier to just do it this way. Yeah, it's a nice trick. But again, you could do it the other way. It's not like difficult. It's just tedious. And I don't know, I'm lazy, so I don't like tedious if I don't have to do it. So then what I do is I take this A inverse, and I could say V, I need to, is equal to A inverse times oops. The vector 1, 2. Any questions so far? Okay, well, if I multiply these guys, I still have the -1/2. And then if I take the 1, 1, -4, -1, 2 times 1, 2, I take the dot product of 1, -4 and 1, 2, and I get -7. And then I take the dot product of -1, 2 with 1, 2, and I get 3. And then I just multiply the 1/2 through. So I get -7 over 2. And it's a -1/2, so that makes positive. And then I get -3/2. Any questions on that? Is that clear, or did I lose you somewhere along the line? Okay, good. And again, that's kind of been my promise this whole class so far, is that it's easy to watch. There's nothing here. There's no hard math here, is there? I mean, to a second grader, for sure, fractions are hard. What's hard is knowing what to do, and that is very hard. But doing it is actually just kind of tedious, just a bunch of arithmetic. And we have a lot of arithmetic in this class, a lot of negative signs. That I can't do anything about. and fractions happen. All right, I think I could do one more. There was a request for 49.
Yeah, you don't have to go too in depth if we could just talk about it a little bit.
Okay, of course, the first thing I have to do is look at it, find out what it is. So I'm, okay, let me. I missed. That's better. Okay, so here's 49. Show that if A is invertible and by a matrix, then so is A transpose, and A transpose inverse equals A inverse transpose. So there's actually two things to do. One is to show that A transpose is invertible. And the other is to come up with the formula. Is that clear? Okay, but what we could do is do it in the other direction. It's a whole lot easier to do the formula and then say, therefore, the inverse exists. So what does it mean for A transpose inverse to be equal to A inverse transpose? By definition, what does that mean?
The inverse of the transpose is equal to the transpose of the inverse.
Okay, that's how you can say it again. But what does it mean? What is inverse all about?
Inverse creates a matrix that when you multiply by the inverse, it creates the identity.
Yeah, and that's what we need to show. Does that make sense? So
Yeah.
what it says is that if we take A transpose and we multiply by A inverse transpose, we better get the identity. Otherwise, it doesn't work. Are you following that, or is that unclear? And backwards.
No, that makes sense.
And remember, with matrices, AB is not BA, so you got to do forwards and backwards. Okay. Turns out if it's square, you only have to do one way, but I don't think we've actually proven that yet. So we'll do forwards and backwards. So what I need to do is I need to take A transpose, and then I need to multiply it by A inverse transpose. Any questions on that? Okay, but we had a theorem about multiplying about A transpose times B transpose. And if you remember, that said that if you have a multiplication of two matrices and each are transposed, then that's the same thing as transposing the backwards multiplication. So that is equal to the backwards multiplication, which is A inverse, times A all transpose. Have I lost? Do you remember that little formula?
Yeah.
It was a nice little formula for transposes. But that's beautiful. Why is that beautiful?
Because A inverse times A is the identity.
Exactly. So that's going to be equal to the identity transpose. But what's the transpose of the identity?
The identity.
The identity, right? The identity is a symmetric matrix. And we're halfway there. Is it okay if I let you do the other half?
Yes, definitely.
And the other half, you have to write A inverse transpose times A transpose. You have to do it in reverse. And you better get the identity when you're done. And then once you've shown that those are true, then we actually showed that that was the inverse, so therefore it's invertible. If you find an inverse, it's invertible, right? Does that make sense?
Yeah.
Right? I can prove that there is a mouse in my room. You want to see how I can prove it? Have I proven it? Yeah, I showed you a mouse, right? And that's a proof. So this is kind of like proving that the inverse exists. I found it. If I found it, it exists. Is that clear? They call that, I don't know if you've heard this, but it's called proof by construction. So that means you construct it and you got it, therefore it exists. Does that make sense? Okay, so anyway, I'll let you do the other way. It's very similar. Okay, so let me get on to the new material. And as you're noticing, you know, there are days when we do one section and that's it. There are days when we spend 3 days on one section, and that's because this book doesn't chunk it very well. Okay, so the next section is by itself. So that's a whole section, whereas we spent like 2 or 3 days on the last one, remember? So I'm just noting about that. All right, so now let us do a big definition of the day. Okay, let's suppose you have a 1-by-1 matrix. Y'all know what a 1-by-1 matrix is, right?
Just a single digit.
Yeah, single, it doesn't be a single digit, but a single number.
Oh, yeah.
Right? It could be, you know, the matrix with the number 1 million in it.
That's way more than one digit. Yeah.
Yeah, but it's still a 1-by-1 matrix.
I always get the words for like numbers confused in terms of like categorization.
Right. So the word for how many things you see in a matrix,
entries, right?
Or yeah, those are
entries. Okay.
Whereas digits are the number of numbers in a number. I guess is a strange way of saying it, but that's basically what a digit is. An entry is what is that? You know, first column, second row. That number is an entry. Do you see how that works?
Yeah.
There's a lot of language in this class. Okay, so here's the wonderful news. The determinant of a 1-by-1 matrix, okay, every 1-by-1 matrix looks like a number, right? Is that number? Is that one of the easiest definitions you've ever seen? Okay, notice though, you know, it doesn't have parentheses around that A. So the determinant is a function. In fact, I'm going to write this down. Note the determinant is a function whose domain is the set of square matrices. And the range is the set of real numbers. Okay, and that's pretty important to note, is that when we say determinant of A, that A on the left is a matrix. And then on the right, that A is a number, not a matrix. So the matrix A is not equal to the number A, but the determinant of the matrix A is equal to the number A. Any questions on that? So here's an example, and just to show you how easy it is. The determinant of the 1-by-1 matrix whose entry is -4 is -4. Is that one of the easiest definitions you've ever seen in your life?
Yeah.
Okay. So
which makes me think it's going to be expanded to be not as easy.
Actually, you're minimizing it. Not as easy sounds too nice.
Okay.
Know that. The 1-by-1 is not a problem. All right, so now I need some definitions to even talk about the rest of them, because we want to say, how do you get the determinant of a 5-by-5? Does that make sense? Or how to determinant of a 100-by-100? So any square matrix has a determinant. So to do that, we need some definitions. So this next definition is the following. So let's suppose A is a square matrix. Okay, we don't, remember I said today, all matrices we're dealing with are square. Okay, then the ijth minor of A. is the matrix that results in removing the ith row of A and the jth column of A. So by the way, this is only true for higher than 1 by 1. Okay, you don't even talk about it 1 by 1 because it doesn't make sense to remove that row when there's only one row to remove. You don't get a matrix and you're done. You get, I don't know. So this is for 2 by 2 or bigger. Just a note. People don't even usually talk about it. It's just kind of assumed. Any questions? So if you start out with a 5 by 5 matrix, and let's say you took the 2, 5 minor, what's the dimensions of the matrix you get?
What was the question again?
So if I started with a 5 by 5 matrix, and then we wanted to find the 2, 5 minor. So what is the dimension of the minor?
2 rows, 5 columns.
Not quite. So let's think about it. We're removing that second row, and we're also removing the 5th column. When you remove those, what are you left with? How many rows?
4
Huh?
A 4 by 4 matrix.
Exactly, a 4 by 4, because you're moving one row and you're moving one column. Do you see that? So if you start out with a 5 by 5, you take a minor, you get a 4 by 4. Any questions on that? Okay. Notice then you have a 4 by 4. If you take another minor, what do you get?
3 by 3.
3 by 3.
3 by 3. So we can keep doing it until you get a 1 by 1. Is that clear? And that's the whole point of this, is we need to be able to use this original definition, how to do a 1 by 1 determinant. And you're going to do it by reducing. Is that clear? Okay, so now we have minor, the next definition. Oh, here's an example, by the way. Here is a 3 by 3 matrix. A is 4, -2, 1, 3, 0, 5, 7, -6, -1. So if I want to find the 2, 3 minor of A, what that means is I take away the second row. So this 3, 0, 5 is gone. Just axe it out. Do you see that? And I take away the third column. The 1, 5, -1 are gone. And what's left is the 4, the 2, the 7, and the -6. So the 2, 3 minor of this matrix is 4, -2, 7, -6. Any questions on that? Okay, as I mentioned, everything we do is easy, but there's so many little details that you got to remember how to do it and when to use it. Do you agree that's easy to do? Okay, so now the next big definition is, let's suppose we have a square matrix, then the ijth cofactor of A, okay, is -1 to the I plus j times the ij minor of A. So this is like a harder definition than minor, because you got to multiply it by -1 to the I plus j. And note, by the way, what values can -1 to the I plus j take?
All real numbers?
Definitely not. -1 to the I plus j is never 7, for example. What can negative? Huh?
1 or -1?
Yeah, 1 or -1. So I wanted to make sure that you're all clear about that. That's not a trick or anything. If you have a -1 to a number, if the number's even, you get +1. If the number's odd, you get -1. So what you really do is you look at where you are, you know, what minor you're looking at. You take those subscripts, add them up. If you get an odd number, stick a negative in front of it. If you add them up and you get an even number, don't bother with changing a sign. Any questions on that? Okay, but you need to have a formal definition of how to do that. All right, so here's an example. Let's suppose we have the same A. Figuring I'll just work with the same matrix because there's nothing special about this matrix, by the way. I just randomly grabbed a bunch of numbers, basically. Then if you want, instead of the minor, you wanted the cofactor, the 2, 3 cofactor of A, well, you're going to take a -1 to the 2 plus 3 times the 2, 3 minor of A, which was the 4, -2, 7, -6. Okay, what's -1 to the 2 plus 3?
-1.
-1. Now, remember that when you do scalar multiplication on a matrix, it means you multiply that number through all of the entries. So the 4 becomes a -4, the -2 becomes a 2, the 7 becomes a -7, and the -6 becomes a 6. So the 2, 3 cofactor of A is -4, 2, -7, and 6. Anyone lost? Okay. If you understand it, it's very easy. Do you agree? Okay. But if you don't understand it, nothing's easy, right? That we're not doing that much. Okay. So what I decided is I want to define the determinant, and I'm going to define the determinant with computer coding, because really that's how determinants are defined. So how many of you have actually done some coding in your life ever of any?
I have in Java.
Okay, so I want to mention that is an important skill. So I'm going to be bringing this in. You're not required in this class to understand or know coding. But if you want to get a good job, you got to know coding if you want, if you're a STEM major, a high level STEM, not just regular STEM, biology doesn't count, but if you're a engineer or whatever, you can know some coding. So again, if you don't understand what I'm saying, that's okay. If you don't understand in 3 years, it's not okay. Does that make sense? So eventually you got to learn some coding, and that's not going away. It's not one of those things where, in 3 years, technology is going to remove that. No one needs to know that anymore. That's not going to happen. Okay. So the nice thing is, let's make a new page so it doesn't split pages. This only took me a few minutes to write the whole code. And this is kind of like JavaScript in a way, but whatever, it's like anything. It's so the determinant is a function. Let's call it det of A. And here's what you do. The first thing is you have an if statement. And you say, if the number of rows of A is 1, that means we have a 1-by-1 matrix, then you just return the value. Okay, and remember, a matrix is a 2-dimensional array, and the way you write arrays in coding is you write your variable, then you do bracket, and then you do row number, you do bracket, and you do column number, and that's a 2-dimensional array. So it looks a little different than the way you do it in math. I thought it was worth showing you this because, again, it's so important to your future, even if it's not officially part of this class. I'm a believer in getting you ready for life instead of just only doing our little class and that's it. And don't go beyond that. Okay. All right. Well, if it is not a 1-by-1, then we have some work to do. So what I'm going to do is I'm going to get a new variable. Some languages make you call it var, some don't. So just det val equals 0. And then we're going to do a for loop. For I equals 1 to I less than the number of columns, I equals 0 to I less than the number of columns of A. In computer programming, You always call it the 0th to start instead of the first. This is one of the weird things about computers. Okay, I++. Actually, that should be J. That was my mistake. See, I had a bug. J++. And then you say, well, we're going to take that determinant and we're going to add the entry, the ijth entry of A. That's what Aij is. And then you're going to take times pow. Pow means you can take a power of -1 to the I plus j. Okay, that's part of the cofactor, right? So you can take the item from the matrix and you're going to multiply it by -1 to the I plus j times the determinant of the cofactor. Any questions on that? And then you're going to keep doing that. And notice when it says det, what that means is you got to go back to the start. And that's called recursive. So again, if you don't know any programming, I encourage you to learn some programming. You won't fail this class if you don't, but you won't get as good a job either. Put it that way. Okay, and then the very end, you return the determinant. And that's your standard program. It's not, not that many number of lines or anything like that. So now let's talk about it if you have no idea what I just said. And that's words. And then if A is 1 to I1, use the number. Got it? Because we already had that definition. 1 by 1 matrix, you're done. You smile. But honestly, nobody ever works with 1 by 1 matrices because they're just numbers. Okay, so if A is not 1 by 1, then take the sum along a row, any row, of -1 to the I plus j times the determinant of the minor. And that's what we do. So let me give you examples now. So again, the words are a bit confusing without an example. Maybe you don't agree. Maybe it's like totally clear to all of you, but let's see an example. And I'm going to do the most important example, which is a 2 by 2, and I'm going to do it in general. It's actually quite easy. So let's do the 2 by 2 general matrix. So the general matrix, and I don't think I've mentioned this yet. You use absolute value type symbols to surround the matrix. And that's not an absolute value, that's a determinant. So if you want to talk about the determinant, write it down. If you have a matrix given, you typically just use those little lines. And that says we're taking a determinant. Whereas if you have just matrix A, you typically write det of A. That's kind of standard. You could put them in absolute values either way. All right, so what I'm going to do, and it turns out I can choose either the first row or the second row. And in this case, the first row is not easier or harder than the second row because it's just 4 letters. Do y'all agree? The first row is AB and the second row is CD. It's not like one is simpler or something like that. But there are many times when one's simpler than the other. Okay. And what I'm going to do is I'm going to start out with this A. So I'm going to take that A and it's going to write A. Then I'm going to say, what's the position of A? Okay. Well, that's row 1, column 1. Do you agree? Now, the easiest thing I'll ever ask you in class, what's 1 plus 1?
2.
2. Is that even or odd?
Even.
It's even. So -1 to the 2 is 1. You following how I got the 1 there? Okay. Then we say, what is the minor? Well, if we get rid of the first row in the first column, all we're left with is D. Do y'all see that? So now I'm going to take the determinant. I'll take the determinant of D. And by the way, this is not the absolute value. This is determinant. Okay, then I go to the next item in the row, which is B. And I write down B. I guess for consistency, I should probably put in parentheses because I did with A. So I write down B. Then I say B is in the first row, second column, right? So that's 1 plus 2, which is 3. 3 is an odd number, and -1 to an odd number is -1. So that means times -1. Again, stop me if I'm lost because I totally understand what I'm saying. That doesn't mean you do. But if there's any step you're not understanding, this is very important to get. Then I take the minor by getting rid of now the first row and the second column, because that's where B sits. And I'm left with just the 1 by 1 matrix C. Any questions on that? Okay, then I just say, well, the determinant of D is D, the determinant of C is C. That was our definition for 1 by 1s. And now just do simple multiplication. A times 1 times D is AD. And B times -1 times C is minus BC. So what we get is that for the general 2 by 2 matrix, its determinant is AD minus BC. Anyone lost on that argument? Okay.
When we find the inverse of a 2 by 2, we multiply by the reciprocal of this, right?
Right. So for the inverse of a 2 by 2, you take the reciprocal of the determinant times the matrix where you switch the diagonals and make the off diagonals negative. Okay. And that's a formula. I think that was a Homer problem formula or something like that, wasn't it? That you had to do. Okay. So I strongly recommend that you memorize this because it's not that hard to memorize. It's probably harder to do 2 examples than it is to just memorize a formula. So AD minus BC. Can you remember that? It's worth it. 3 by 3, there is a formula, but it's much messier. So that's one I don't recommend memorizing. And do you think there's a formula for a 5 by 5? Sure. Good luck. You have an amazing memory if you can memorize it. I don't expect anyone to be able to do that. I don't have it memorized, but I know how to do one. Any questions on the process? Okay, so let's look at a 3 by 3. Okay, so here's a 3 by 3, and it's 412, -501, 131. And what I want to do is I want to find the determinant. So let me tell you the first step. The first step is to see if you can find the way to do it that takes the least amount of work. In this matrix, what's the easiest number of all the 9 numbers?
1.
No, easier.
0.
0. Because remember, you're multiplying. And if you have 0 times something, you don't even have to worry about what the something is. So what I strongly recommend doing is seeing if there's a row that has 0 or maybe many zeros. That's even better. Does that make sense? And if there is, use that row. You can use any row you want. Okay. And so in this case, do you all agree that the second row is going to be the easiest row? And we'll see how that works. So now I'm going to take the second row and I'm going to expand the determinant by the second row. Do you see that? So I take -5, I write it down over here. And then I say, well, -5 is second row, first column. Got it? 2 plus 1 is 3. And 3 is odd. So that means I put a -1 in. Any questions on that? And then I take the minor, which means I get rid of the first column and second row. And I'm left with 1, 2, 3, and 1. Anyone lost on that? Okay, then the next item in that row is 0. And the good news is I don't need to even do the rest of that. How come? Well, I don't even have to bother with whether it's -1 or +1 and what's the minor. You see it? Maybe I'll write it different. I don't see y'all jumping in because it's 0 times stuff. And the key is, I don't care what the stuff is. What's 0 times
multiplied by 0, so
Yeah.
it doesn't affect anything.
Exactly. 0 times stuff is 0. I don't care what the stuff is. So this is why it saves a lot of time to pick a row with zeros in it. Do you see that? How did I get the 3 and the 1 on the bottom? So what I'm doing is I'm taking the, so it's -5. So I'm crossing out this second row, and I'm crossing out the first column. Does that make sense? So if I cross out the 4, -5, 1, the -5, 0, and 1, I'm left with 1, 2, 3, 1. Does that make sense? Okay. So for the next one, I don't even care because it's 0 times stuff. And I'm not going to spend my time finding the stuff because don't you agree? It's totally wasting your time when you don't need to. On the other hand, for the third element of that row, it's a 1. Okay, and 1 times stuff is stuff, so you need the stuff. Stuff doesn't go away. So we're going to do 1. And now this 1 is in the second row, third column. Got it? 2 plus 3 is 5. And then 5 is odd. So that means you have a -1. Okay, then I find the minor associated with that second row, third column. So I get rid of the third column, I get rid of the second row, and I have a 4, a 1, a 1, and a 3. Any questions on this? Okay, once you get used to this, it won't take as long as what I'm taking, but I'm trying to explain every little step. All right, so now I'm going to do some arithmetic. -5 times -1 is 5. Hope you're all okay with that. Then we got to take the determinant. Now it's a 2 by 2, and I've memorized that one. That's 1 times 1 minus 2 times 3, or 1 minus 6. Plus 0, so I can ignore it. And then we have a 1 times a -1 is a minus. And then 4 times 3 is 12. Minus 1 times 1 is 1. Anyone lost on that? And now it's truly baby arithmetic, right? Maybe not baby, but elementary school arithmetic. And that is 5 times -5 is -25, minus 12 minus 11. So that's -25 minus 11 is -30, is -36. Oops, lost a negative. Any questions on the determinant? All right. Imagine doing a 200 by 200 matrix, finding a determinant. Could you do it?
It takes some time, but yeah,
How do you think I did it? Because I've done it.
with a computer.
I wrote a program. Yeah, no, you would never do it by hand. You would write a computer program code to do it. And then I made it fancier because it crashed the computer. So I needed to actually write some code to actually make it go faster than the standard code. But that's a long story I'm not going to get into. There were enough zeros that I can, do some quickening stuff. Okay, but this does happen. This does happen. Any questions at all on this example? Any questions? Okay. I think it's worth it to have you guys try one. I think it's important for you to be able to try one, then ask questions if you get stuck on anything. So let me just throw one in. All right, let's see if you can find the determinant of the matrix 1, negative 1, 3, negative 2, 1, 1, 1, 3, 0. And it shouldn't take more than a couple minutes, but I think it's worth it to practice while we're actually, doing this. And if we were in a face-to-face class setting, I'd have you do the same thing. The difference is I'd be walking around looking at your work and helping you. Now I can just answer questions that you post on the chat or ask. And let's see if I can do this in my head. Okay, got it. And when you got it, see if you can post your answer in the chat box. Should be a number, by the way. Can get a couple answers. Let's see if at least 2 of you can agree. Okay, negative 25 is what I did in my head. I don't trust it when I do it in my head, by the way, because that's a lot of like craziness in the brain. But yeah, it's negative 25. So hopefully you're all getting that. And Victor, if you see if you can find your little mistake. My guess is you're off by minus sign. That when you did the 3, that this is a negative 3 here, because it's positive, negative, positive, negative. It's the third row, second column. 3 plus 2 is 5. That's negative. So it's negative 3 times 7, which is negative 21. So my guess is you did positive 21. I can't tell you for sure, but that was my guess. Any questions? You feel comfortable that you can do a determinant? Do you feel comfortable you wouldn't want to do by 10 by 10 by hand? Okay, so now that we know how to do determinant, let's do some special ones. So first thing, some definitions for you. They're nice, easy definitions, by the way. So a matrix A is called upper triangular if aij equals 0 for all I greater than j. So that means that kind of the bottom part are all zeros. Below the diagonal is all zeros. And A is called lower triangular if aij equals 0 for I less than j. So that means the upper part is all zeros. And if A is either upper triangular or lower triangular, in general, we just say A is triangular. Any questions on this definition? Nothing too fancy about it. Okay, and the reason if you have one, it looks like a triangle. That's why it's called triangular. Okay, now comes the big theorem. And that says if A is a triangular matrix, then the determinant of A is the product of the diagonals of A. And that makes life so nice. And the reason why that works is the following. So let's look at this example. So do you all agree this is a triangular matrix? Do you see the triangle involved? Everything below the diagonal are all zeros. So that means that if I is greater than j, you get 0. Right? If your row number is greater than your column number, that means you're 0. And if I want to find the determinant of this matrix, I don't have to do any of that definition stuff. I just go 1 times 5 times 1 times -1, -5. So do you agree that triangular matrices are wonderful for determinants? Okay. The reason why it's true, I don't think I'm going to prove the full thing, but I'm going to explain why it's true. So if you wanted to do this using the definition, how would you start? Which row would you pick?
I'd pick row 3
Row
3?
4. Row
or
4.
4.
How
Yeah,
about row 4?
yeah, that's what I meant.
Okay. Yeah, row 4 is definitely what you want to pick. And the idea is you have 0, 0, 0. And when you get to the bottom, no matter whether it's a 10 by 10 or a 4 by 4, the point is if you're on the diagonal. And if you're on the diagonal, row and column are the same, right? In this case, row 4, column 4. And 4 plus 4, even if it was 10 plus 10 or 18 plus 18 or 21 plus 21, will always be even. If you're on the diagonal, I plus j is even because it's I plus I, which is 2I. So what you get is you just get this number, -1, times the matrix, the determinant of this 3 by 3 matrix. Do you see that? Okay. And yeah, you got to multiply by 1, but multiply by 1 doesn't do anything. So we just have -1 times the determinant of the 3 by 3. But now we can use mathematical induction and say we're done. If it was 20 by 20, then the very last row, you just grab that number, multiply by the determinant of the 19 by 19, but the 19 by 19 would be a diagonal matrix, a triangular matrix. So proof by induction. Okay, I know I said it instead of wrote it down, but I only have so much time in the class. Any questions on that proof? So it's a quick induction proof. And by the way, 1 times 5 times 1 times -1 is -5. And that's it. Isn't that great? Okay. Now some more theorems. So now let's do a row operation expiration. That means you're going to have to do some work. All right, so I have this matrix. And the matrix, and this should determinant, I guess, is -36. If I did this right. Plus, yeah. Was that right? Is this that same matrix? No, it's 36. Let me go find it. Let's see. No, it was negative. Am I off by one? Positive, negative, positive. Yeah, it should be negative 36. Sorry about that. So determinant is negative 36. Okay, so let's suppose we have this matrix. And what I want you to do is I want you to perform the row operations that you're assigned to. So you're not ready to do it yet. And find the determinant of the result. So there are 7 of you here. So listen to your name and number. Got it? So Cesar, you're 1. Bradley, you're 2. Jordan, you're 3. Jacob, you're 4. I'm sorry, you're 1. Victor, you're 2. Ralph, you're 3. And Jesus, you're 1. Got it? So hopefully you paid attention to the number I gave you. And what I want you to do is I want you to perform the row operation. Remember, row R1 was switch rows. R2 is multiply a row by a non-zero constant. And R3 is think about a row. We're going to replace a row by that row plus a multiple of another row. So what I want you to do is I want you to do the row operation that I told you, and you could choose, like at switch rows, you could choose which ones you want to switch. I don't want you to multiply by 1 because that's too boring. if you're a number 2, so any number other than 1, and if you're R3, again, pick a row, add a multiple of another row, and make it happen. So I can give you a minute to do that, and then find the determinant of the matrix you get, and tell me what you noticed. So this will take a few minutes. And when you're done, tell me what happened to the determinant. How did it change or how did it not change? And you can pop that in your chat box. And hopefully you agree with the other person or 2 people if you're number 1. So there were 3 of you. All right, so Jacob had the number 1, which is switch 2 rows. and it multiplied by -1. Switch signs. We'll see if that worked. So -36 became 36. But I like just saying switch signs because that's more important. And Cesar, did you had number 1 also? I think so, because you're first on my view. So did the same thing happen for you? You switched signs? Yeah. And Jesus. Okay, so the number 1 people, you all finished first. It was interesting. 1 finished first. And you all said you switched signs. Okay, no matter which rows you picked. I didn't even tell you which ones you had to pick. You got number 2, you multiply by 2, and the result was multiply by 2. Okay. You got 28. All right, Bradley, I'm worried about that. You got row up 2, you multiply by 2. But I don't know if you got 28 on that. 36 times 2 is not 28. And I want to make sure that we have at least someone from each group. So we haven't gotten a row op 3 yet.
So it must be just a sign issue because I have 50 minus 22 instead of 50 plus 22.
50 minus 22. Yeah, you lost a sign somewhere.
Yeah.
You could look at your writing. Hopefully you wrote it down and you'll find your mistake. Because if you multiplied a row by 2, I promise you, if you did it right, you should get -72. So it should be -50 minus 22, actually. So the sign is in the 50 part. But I haven't heard anything from row op 3 group. There's 2 of you. Aha. Okay, so Ralph got -36. So what changed? For your row op 3? How did it affect the determinant? Yeah, nothing. You started with 36. You did row op 3 and you got 36. -36, sorry. Started with -36, you did row op 3 and you got -36. Okay, so I am going to now state the big theorem. And this is a really important one. And it says the following. So it's 3 parts. And you might guess why there's 3 parts, because there's 3 row ops. And it says that if you switch rows, the determinant gets multiplied by -1. And then if you multiply a row by a constant, that's going to multiply the determinant by that constant. And then if you do a row op 3, if you replace a row by the sum of that row and a multiple of another row, there's no effect on the determinant. You end up with the same number. So that's a very important theorem. Let me boldface it because it's that important. So it does stuff sometimes. For 1 and 2, it does stuff. For 3, it does nothing to the determinant. Any questions on this big theorem? I'm not going to prove it. I decided I thought it'd be more valuable for you to try it yourself and see it than for you to watch me prove it. But it's provable. It's messy, a lot of subscripts. This is the way you prove this, but you can trust me. Sound good? Okay, so now we have the following big theorem. This is gigantic and it's easy. Okay. Very important theorems are usually easy to remember. And that is, if you want to take the determinant of a product of two matrices, the determinant of A times B is equal to the determinant of A times the determinant of B. Okay, do you agree that's easy to remember? Okay, the proof's messy. I don't have time, I don't think, to prove it because we only have 29 minutes. But maybe I'll prove one of these theorems if you want to see a theorem, but I can't prove every theorem. But they're all in the book and the proofs are all there too. So that's a big deal. So if we happen to have a product, it's very easy to deal with the determinant. You just do one at a time and multiply, and multiplying is easy. Any questions on this big theorem? Okay, now the next theorem. And that is the determinant of A transpose is the determinant of A. Isn't that a beautiful theorem? So the determinant of A transpose is the determinant of A. So for example, by the way, let me give you an example. If I wanted to find out the determinant of let's do a 4x4, make it really miserable. Takes a moment to type them out. And I want to find that determinant. Looks ugly, doesn't it? I can do this in less than a second. Explaining will take about 10 seconds or 20 seconds. How would you do this? Okay, the first step is to take the transpose. Because taking the transpose doesn't change the determinant. You got it? Now, if you take the transpose, then the third row is the row of zeros. Do you agree? Because in A, the third column is a column of zeros, and transpose switches rows and columns. Do you see that? So now I'm going to expand by the third row. 0, 0, 0, 0, I'm done. The determinant is 0, I'm done. That's it. Isn't that beautiful? I can do the whole thing in my head with nothing to do. It's just 0. If I have a column of zeros, the determinant must be 0 because I can take the transpose and expand across that column, that new row that used to be a column. And it says 0 times stuff plus 0 times stuff plus 0 times stuff plus 0 times stuff. So the determinant is just 0. Isn't that beautiful?
If we weren't to use the transpose, if we were to brute force it the other way, it'd still be 0.
Yep. But why would you want to do that?
I don't know. I was just curious. Though.
But if you wanted, if you were masochistic, then you would get 0. But the key is you can look at this and know immediately the determinant is 0 because we have a column of zeros. So you can always take the transpose first and then find the determinant, and that won't change it. Do you see that? Isn't that beautiful? Okay, so that's this theorem, and one of the big uses of it is that. Okay. Any questions on that? Okay, now next theorem is the determinant of A inverse is 1 over the determinant of A. Why is that obvious? Why must that be true? Let's prove that one because it's an easy proof. What's the definition of A inverse? What's the definition of A inverse? You're all supposed to know this. We actually did it on one of the homework problems you asked today. So I've already done it today.
A inverse times A is the identity.
Exactly, exactly. So that's the first thing. I'm just going to write that down blindly because it's going to work. So A inverse times A equals the identity. Sound good? All right, well, I want determinant. So what can I do to both sides?
Take the determinant.
Yeah, I know. It's kind of obvious, right? But that's what I need to do. And we know that's true. Any questions on that so far?
Could you scroll up just a little bit?
Sure. Is that enough?
No, the other way, just a little bit. Sorry.
Okay.
Like earlier into the document.
That way.
All right, cool. Thank you.
Okay. Yeah, I never know exactly what you can see. Sorry about that. But let me know if you can't see something. All right. Well, what's the determinant of A inverse times A? What can I do? Because I have a big theorem that I already wrote down. I didn't prove it, but we'll pretend we proved it.
It's the identity. Or
Mm.
1.
Yeah, but that's not going to help because then I get the determinant of identity equals the determinant of identity. I already know that.
Mm.
But what about when I have a product of two matrices?
Oh, we have the determinant of A inverse times the determinant of A.
Yeah. So I can write that as determinant of A inverse times the determinant of A. What's the determinant of identity?
1.
That's 1, because the identity is a triangular matrix such that all the diagonals are 1. 1 times 1 times 1, no matter how many times you times 1, you get 1. So the determinant of identity is 1. And now, notice the determinant is a number. Got it? So I have this number, determinant of A inverse, times this other number, determinant of A, equals this number 1. And I want to get the determinant of A inverse by itself. Now, when you have numbers, I can use algebra, like basic algebra. And I could just divide by the determinant of A, and I'm done. And you get the answer. Right? You can't divide by matrix, but you could divide by a number is always allowed. As long as the number is non-zero, but it's non-zero because just by writing A inverse, that means that it's invertible. And if it's invertible, it can't be 0. Well, it can't be 0 anyway, because if it was 0, we'd say 0 equals 1, and that's a contradiction. So I'm allowed to divide. And that's the proof. Isn't that beautiful? Okay, easy to watch, isn't it? But if I asked you to do it without showing you, that might be a little different. Any questions on this?
So what does the determinant actually mean?
Okay, well, I showed you the definition,
Mm-hmm.
but that's not what you mean, right?
No,
Like,
I mean, like what is it used for?
geometrically.
Yeah.
Okay, so let me give you an idea geometrically. And the idea geometrically is if I start out with a figure and I apply the matrix to all the pixels of the figure, got it? Then I'm going to get a new figure. The determinant tells you how much shrinking or expanding happens when you do that transformation. And when did you learn that?
Jacobians.
Yeah, that was last quarter. So you've actually had it before. Okay, so if you want to know what it means geometrically, that's what it means geometrically, is it tells you the shrinkage or expansion of any figure. Okay, zoomed in at least. That make sense? So that's what it means in that case. Now, if the determinant is 0, then you're actually decreasing a dimension. So if we started with a 4x4 matrix and determinant is 0, then you went from a 4-dimensional object to a 3-dimensional object, or lower even. So there's some more to it. If the term is non-zero, that means you don't decrease the dimension. So those are some geometric properties. Okay, and we'll be talking about that later. I actually I wrote an app for that that we'll play around with, 2x2 though. Okay, let's see how are we on time. Not sure if we have time to actually do one of these, but it can be done. Okay, why are these theorems helpful?
Because we might run into a situation where doing it, say the first way you showed us, is not a good option.
Right. So let me show you another way. So I'm going to not do this because we only have so much time. We only have 18 minutes. Oh, actually, maybe I guess that was good. Okay. Yeah, actually, that's the next day. All right. So what can we do? Well, how do you find this messy determinant? What can you do? Any thoughts? Okay, what you can do is you can RREF. Okay, I know that's what you're all thinking, but you pay attention while you're RREFing. And here's what I mean by paying attention. What you do is you say, I'm going to RREF this matrix, and every time I do something, I'm going to see how did it affect the determinant. Does that make sense? And the idea here is when you RREF a matrix, that's multiplying a matrix by an elementary matrix. Does that make sense? Do you remember that from last time? So for example, what's the first thing you're going to do to RREF this matrix?
Which row?
Right, you're going to switch rows. Which rows are you going to want to switch?
1 and 4.
1 and 4. So I'm going to switch 1 and 4. Let's do that. And I get 1, 4, -2, 3, and row 4 becomes 0, 2, 3, 6. All right, but I have to be careful. Have I changed the determinant?
Potentially, yes.
Yeah, how have I changed it?
The sign.
The sign of it, yeah.
Right. So what I'm going to do is the following. I'm just going to keep track of what I've done. I'm just going to put -1 there. I just multiply by -1. Do you see that? So it's important to keep track of what you've done because we're going to have to see it at the end. Because what we get at the end is not going to have the same determinant necessarily as what we started with. Is that clear? But if you keep track, you're going to be able to adjust. And it's just adjusting simply, like multiplying by -1 is an easy adjustment. Okay, then what can I do? Oops.
You can add row 1 and 2.
Yeah, and I'm going to do a couple things. I'm going to add row 1 and 2 and replace row 2 with it. I'm also going to multiply row 1 by -2, add it to row 3, and replace row 3 with that. Now, what's the effect on the determinant when I do that? There's row op 3.
Nothing.
Nothing, right? So if you had a number 3, then you should know that, right? If you didn't and you were paying attention, then you should know that too. So the good news is I can do those row ops and not even worry about keeping track of the determinant. So let's do them. So that -1 becomes a 0. That -5 becomes a -1. This 2 becomes a 0. And this -1 becomes a 2. Any questions on that? And similarly, I'm going to double row 1, add it, multiply by -2 to row 1, add it to row 3. And when I do that, I get 0. That's the whole point. And then -2 times 4 plus 7 is -1, right? -2 times -2 is 4 plus 1 is 5. And 3 times, let's see what we were doing now. 3 times -2 is -6 plus 4 is -2. Any questions on that? And just to keep track, I'm just going to write ×1 just to remind myself. The second thing I did, adjusted the determinant by multiplying by 1, which doesn't adjust. Just kind of helps me so that if I make a mistake, I can see where it came from. Does that make sense? So I'm going to write ×1, which means I didn't change the determinant. Any questions so far? Okay, now what am I going to do?
Multiply row 2 by -1.
Good, good. I'm going to multiply row 2 by -1. When I do that, what's the effect of the determinant?
So you multiply the determinant by the same constant.
Right, and in this case, -1. Do you see that? So I'm going to put a -1 there. Again, I'm keeping track. And that -1 becomes a +1. This 2 becomes a -2. Is that clear? Okay, now that I've done that, let's do the next step. Oops. That's better. Okay, what's the next step?
Multiply row 2 by 1, add it to row 3.
Exactly. Okay, so I'm going to do that. You get a 0 for that -1. The 5 stays a 5. And the -2 becomes a -4, right? Any questions on that? And then I like to do both at once because we're not changing the determinant by doing this. The third row op, we're just multiplying by 1. Okay, so then I'm going to take the row 2, multiply by 2, or multiply by -2 and add it to row 4. That 2 becomes a 0. The 3 stays a 3. And the 6, well, we have -4 and then plus 6. Sorry, we get, 4 plus 6 is 10. Any questions on that? Anyone lost? Okay, now I keep going. I have a 5 there. What would I like it to be?
1.
A 1. So what row op do I do?
Multiply that row by 1/5.
Multiply row 3 by 1/5. So that changes the determinant because now we're doing row op 2 You're going to multiply the determinant by 1/5. Got it? And when I do that, that 5 becomes a 1. The -4 becomes -4/5. Any questions on that? Okay, and then the next step, which is our last step, in the row ops at least, is to do what?
Multiply the second one by -4 and add to row 1.
Okay, so one thing is, I understand what you're saying, is you're RREFing. You don't need to RREF.
So divide the 4 by 3.
We just need to REF because we don't need it. We only need it to be triangular. We don't need it to be diagonal. Got it? Does that make sense?
Yeah.
So it's not wrong to make that 4 a 0, but it's a total waste of time. Because I just want it to be diagonal. Sorry, triangular, and that's good enough for me. So what's the number in this matrix that's keeping it from being triangular?
It will be the 3.
in row
The
4.
3. This 3 over here needs to be a 0. Do you see that?
Yeah.
So now I'm going to multiply row 3 by -3 and add it to row 4. And when I do that, that's row op 3. So that's multiplied by 1, the determinant. That 3 becomes 0. And then if I multiply, it gets a little messy, but it's not so horrible. If I multiply -4/5 by -3, I get 12/5. Add that to 10. So that's 62/5, right? So I made sure that only the last step had ugly fraction. If I did it in my head right, then that should work. All right. Now I'm in really good shape. I don't need to do any more row ops. What's that determinant?
62/5.
Exactly. It's 1 times 1 times 1 times 62/5. Maybe I'll write that out just to like scream at it.
And then don't we need to also multiply our other stuff?
Right. So I found the determinant of this last matrix. I did not find the determinant of our initial matrix. So at least I got this, right? This is not the answer to the question. This is the determinant of the last matrix. And 1 times 1 times 1 times 62/5 is 62/5. But that is, again, not the determinant of the original. And I'm going to do this multiplication out also. And if you take -1 times 1 times -1 times 1 times 1/5 times 1, I get 1/5. Any questions on that? Which means if I started with the determinant of A, then all of these row ops have the effect of multiplying by 1/5. Is that clear? So that means 1/5, let's write this out. So that means, get some more space in there. So that means 1/5 times the determinant of our matrix, I'm just going to call it A, is equal to 62 over 5. Have I lost anyone on that idea? And now it's really easy. So what's the determinant of A?
Would it be 62?
Yeah, 62. Multiply left and right by 5. Hopefully that's easy for you. Is there any questions at all about this example? Notice this is a very, very different way of finding the determinant than using the definition. Do you all agree? This is
So we can do either one. It just depends on how we feel going in.
Yeah, and this is what it has to do with practice. Is that if you practice a lot, you'll get used to which one's easier. You'll be able to look at a matrix and say, I think this one is good to be done with RREFing, whereas this other one is better to be done with the definition. And a lot has to do with how many zeros there are. Because if you have a lot of zeros, then the definition is much easier. You just expand by that row that had a lot of zeros, and it just cuts it. Does that make sense? Whereas if you don't have a lot of zeros, and it turns out, this isn't in the book, but it's a nice word. A matrix with a lot of zeros is called a sparse matrix because it sparsely has non-zero stuff. So that's just a note. But it takes a while to get used to. But here's the thing: you should know how to do both, because in proving things, sometimes you do one, sometimes you do the other. So, for example, how do I know that if I have a matrix, a square matrix, where 2 rows are equal, repeated 2 rows, how do I know what can you tell me what the determinant is? If you have 2 rows that are the same, what's the determinant? Think about it. The hint is it's very easy. I don't see you all jumping in.
Would it be 2 times the original value?
That's much easier.
Would it be 0?
It's 0. Because if 2 rows are equal, you could do the row operation that says take -1 times the first row, the first equal row, add it to the second row, and guess what? You get a row of zeros. Do you see that? And if you have a row of zeros, we already saw, that means that you have a determinant of 0. So if you have equal rows, any 2 equal rows, even if the rest of them are all messy, then you always have a determinant of 0. Is that cool? So there's all kinds of things. So, for example, if you have an idempotent matrix, can you tell me what are the possibilities for the determinant? Now, who remembers what idempotent is? It was on your homework. Can you remember?
A squared equals A.
A squared equals not A, but I. So A squared equals the identity. Right? Was it A or I? Sorry about that.
No, I think he's right. I think it's A squared.
That's A squared equals I. A squared equals A, sorry. So if A squared equals A, then what do you know? Well, if you take the determinant of both of those, that means the determinant of A times the determinant of A is equal to the determinant of A. Well, you could divide by the determinant of A, and then you get the determinant of A equals 1, or the determinant of A equals 0. Do you see how that works? So there's all kinds of stuff you can do. Figured I'd finish off in the last 1 minute I had, because we're out of time. So I'm going to stop the share. And I am going to stop the recording.